Hello and welcome to the representation for the article with title Blind Image Quality Assessment based on multi-resolution local structures. Image quality assessment is very important nowadays with the ever-increasing growth of digital cameras and intelligent mobile phones. Digital images have become an increasingly important medium. Digital images are usually distorted through acquisition process, transmission through a noisy channel, or by applying some process. Therefore, in order to confirm, control, and enhance image quality, identifying and quantifying image quality is important. Image quality assessment methods can be classified into subjective and objective approaches. Subjective approaches are based on human and are time-consuming. But on the other hand, the aim of objective IQA is to design mathematical models that are able to predict the quality of an image accurately and according to the human perception. Based on the availability of the original images, IQA approaches are classified into three classes: full reference, no reference, and reduced reference. In full reference approach, the original undistorted version of image is accessible as reference image and can be compared with the distorted image to compute their difference and check their quality. In no reference or NR image quality assessment, image quality is assessed without any access to the reference image. And finally, in reduced reference or RR image quality assessment, the distorted image and some additional properties of the original image is provided. In our proposed method, the input image is taken by the user, and after subsampling, the gradient of the image is computed, and afterward some features are extracted from from the input image, its subsampling version and its gradient, and after that Gaussian mixture model is fitted on these features, and finally a neural network with parameters of GMM is trained to predict the quality of the image. Initially, the image is converted from RGB color space into LAB color space. This is due to the fact that in LAB color space, illumination and color information can be separated. To extract the features, initially the image is divided into non-overlapping 8x8 blocks. Afterwards, local standard deviation and local entropy is calculated for each block. The formula for calculating these features are shown here. After calculating the mentioned two features for each image patch, a Gaussian mixture model with two components is used to represent each feature. Gaussian mixture model is one of the most useful and efficient methods in modeling a variables distribution. These models are a weighted combination of Gaussian function that model probability density function. Here we used two components for GMM, therefore entropy's distribution is described with four parameters: mean and standard deviation, each Gaussian component. To describe local standard deviations distribution, this process is repeated. Overall, 8 features are extracted. In order to detect multi-scale information, two different scales with subsampling rate of 2 are used. The subsampling process uses bilinear interpolation to approximate the pixels and avoid aliasing. Also, the same process is repeated for corresponding gradient images. Image gradient shows the local changes in image brightness. These gradients are calculated in two directions by using convolutions of Sobel operator. After extracting image features in all scales and their corresponding gradient image, a vector of 32 numbers are obtained as features. In final stage, a multi-layer perceptron is used in order to estimate image quality scores using extracted feature vectors. Furthermore, another multi-layer perceptron is used to classify distortion type. Both of the networks consist of an input with 32 neurons and a 10 neuron hidden layer. In the last layer, the regression network uses a continuous neuron with linear activation function, and the classification network uses 5 neurons with sigmoid activation function. In order to train the network, extracted features and their corresponding image score are given to the network as input and desired output respectively. To evaluate our proposed method, we use live dataset. This dataset consists of 5 distortion types, namely JPEG compression, JPEG 2K compression, Gaussian white noise, Gaussian blur, and simulated wireless channels bit error. Live dataset includes 779 images, some of which are shown in figure below. Subjectives rating are DMOS in the scale of 0 to 100. We use 3 metrics to evaluate the performance of our algorithms: Pearson correlation coefficient, Spearman correlation coefficient, and root mean square are used, which the formula for each of these metrics are shown here. The figure shows the regression line. As you can see, the regression coefficient is 0.95, which is very good, and it shows that the model can predict the quality of an image with a good accuracy. Also, this table shows the value for 3 metrics for different methods, and you can see our proposed method have achieved a good score in 3 metrics. Also, in this table, you can see the confusion accuracy for different type of distortion, and for 4 different methods, including our proposed method, which you can see for most of the distortion type, our accuracy is higher than the other articles. Thank you for your attention.